This video is on calculating truss forces, and for best results, I suggest that you watch this video on a computer rather than your phone, and approach this video as a lecture on material you will need to know. And especially for this video, you should have some pencil and paper ready. You should be prepared to stop the video often and jot down notes. Jump back and forth using the J and K keys as needed, and actually do the calculations that I describe, but don't go over in a step-by-step manner. So let's get started. We're going to talk about forces and how they act on a truss bridge. And we know that there are two types of forces, compression and tension. Compression is when a body is being squeezed, and tension is when a body is being pulled apart. So each member, which we'll define shortly in a truss bridge, is in either tension or compression, will be one of our assumptions. So a truss is something you're probably familiar with. A truss is composed of slender members joined together at their endpoints, and they're usually joined by welds or gusset plates. So that picture on the previous slide enlarged shows that we have these members here. They can be fairly complex, as you can see, or they can be more simple. And the gusset plates here bring together at a point the various members. For example, this one and this one, and then this one, and this one. You can see these two are very different. This one's big and beefier, this one's a little smaller, and the gusset plates brings them together at a point. And of course we have this one here, which is also part of that joint. What is a simple truss? Well, a simple truss is composed of triangles which retain their shape even when they're removed from supports. So triangles are very special. They're very strong, and let's remind ourselves why that's the case. If we try to make a truss out of rectangular geometry objects and we hit it with a force on one corner like this, it's going to shear like that, which is no good. However, if we do the same and we put a cross brace there as shown diagonally, and we hit it with a force up here, then it resists shear deformation. Pinned and roller supports. So all of our bridges are going to be supported at their ends by a support, a reaction force of the earth on the bridge. And there are two types. There's a pinned support, and a pinned support can support a structure in two dimensions. And by that I mean it will apply a force in the horizontal and the vertical direction. It really pins down that edge of the bridge, that end of the bridge. In contrast, there's a roller support, and a roller support can support a structure only in one dimension. The most relevant one is shown down here, and it will support the end of the bridge vertically. It won't come crashing down into the earth, but it will allow it to move horizontally. So it only applies a vertical reaction force. This is a symbol for a roller support, and this is a symbol for a pin support. So we're going to solve truss forces. What are the forces on these members that make up the bridge? And we're going to make some assumptions. First assumption is that all members are perfectly straight. Second, all loads are applied at the joints. That's where we're going to analyze the forces. We're not going to analyze forces within the members. All joints are pinned and frictionless. Each member has no weight. We know that's not the case because we're making these out of steel, so they're quite heavy, but the idea is that the weight of each member is significantly less than the loads of For example, many vehicles exceed the force of the weight of a particular member, so we're going to neglect it. And members can only experience tension or compression. So there's a thing called static determinacy, and a statically determinate structure is one that can be mathematically solved. And the equation is 2j equals m plus r, where j is the number of joints in the bridge, m is the number of members, and r is the number of reaction forces at the ends of the bridge, where the earth provides that reaction to the bridge's weight so that it doesn't, again, fall toward the center of the earth. We support the bridge there. So this is a statically indeterminate truss. We have our triangles, so that looks very truss-like. We have two pinned supports at the edges. But what we'll find is that this is statically indeterminate. We can't solve it. So a truss is considered statically indeterminate when the static equilibrium equations are not sufficient to find the reactions on that structure. There's simply too many unknowns. So if you count up the number of joints, members, and reaction forces, you'll find that they don't add up, and we'll see why in a minute. So the way I like to think about this is if you're making a sketch in a 3D CAD software program, or maybe any CAD software program, you can over constrain it, in which case you're not able to continue to specify dimensions in that case, because it's already so wound up, so to speak, that it can't really move and do anything. So that's the way I think of a statically indeterminate situation, and it seems like a good analogy here. We'll find out that these pinned supports don't allow this bridge to do anything. It's completely pinned, so we can't analyze any of the forces in the members. However, if we relax the reaction force on the right, the supports on the right, and make it a roller, and so then we lose one reaction force. Formerly we had 4 here, up and down, left and right, up and down, left and right. Currently we just have up and down, left and right, and up and down. So we've reduced that to 3. Up and down is one force, one reaction force. So this is a statically determinate truss, so we can go in and then find what the compression and tensile tension forces are in the truss. So this is a static determinacy example, and there are so many bridges out here. They're usually quite old, because now we make most bridges with concrete, which has its own pitfalls, but nonetheless it's cheaper generally, I think. However, let's look at this bridge. It's a Main Street bridge in Brockport, New York, and it has 19 joints, 35 members, and 3 reaction forces, a pin and a roller, making it statically determinate. 38 equals 38. Okay, the equilibrium equations that we're going to use to analyze our truss bridge are the following. We're going to make sure that the sum of the moments around a point sum to 0. In other words, the thing is not going to try to rotate on us. So we know that written out in equation form that we can access, that's the sum of m equals 0. Recall that capital sigma means to sum up all of what's in front of it. M represents the moments, or the torques around a point. Those have to sum to 0. Also, since force is a vector, it's got an x and a y component. We'll be doing these things in 2 dimensions. The sum of all the forces in the x directions must equal 0. Similarly, in the y direction, the sum of all the forces in the y direction must equal 0. So let's do a quick example, and this is where you might want to write out this truss and get down in the weeds and do the calculations yourself. I'm going to hit them at a higher level. This is our statically determinate truss, and we know that because over here at point C we've only got a reaction force that goes straight up. We don't have a reaction force that goes horizontally as we do over here at A, and the notation can become a little cumbersome. We want to identify each joint on the bridge as with a letter so we can tell them apart, but then we need to have some subscripts to tell where we are. For example, this is the reaction force at point C in the y direction, so we've got a subscript. This is a reaction force at point A in the y direction, and so on and so forth. I don't think it's too big of a burden to deal with the notation. It's really not that bad. But one thing we need to know first of all is how big the thing is. So we know this is 7 feet and 3 feet here. We've got a force of 500 pounds right at this joint, presumably due to perhaps a truck sitting right here. So F sub D contributes a negative moment because it causes a clockwise moment about point A. So if we look at point A and we calculate the sum of the moments around that point, then we look at all the forces that act on the system that are extended away from A. D is the first one. It's going to cause it to go clockwise, and that's a negative moment. Okay. Then RCY, which is pushing this up here, clearly is going in the opposite direction, and so it contributes a positive moment because it causes a counterclockwise moment around point A. So if we apply one of our equations, the first of the three, the sum of the moments about a point A, and really we can choose any point. Some are much more convenient than others. Any point, that is, to sum the moments. We're going to choose A in this case. So on the left side of the equal sign is this. So we've got minus FD times 3 feet. Distance here is 3 feet. These are at right angles to each other. Plus RCY, a total of 10 feet away, that must equal 0. So I put in the numbers and I find that with a little arithmetic, I have one equation and one unknown, and I find that RCY is equal to 150 pounds. So that'll be a common calculation that we'll use for the reaction forces. This is actually the easier part of the calculations. So again, if you're doing this on the paper, a force that causes a clockwise moment is a negative. A clockwise motion is a negative moment, and counterclockwise is positive. That's by convention. Sum of the y forces to find RAY. So if you think about it, the red arrows are the ones that we don't know. So we used to not know this one, but we applied our moment equation to find this one. To find these two, we're going to have to get out the other two equations, and the first one we're going to use is the sum of the forces in the y direction must sum to 0. So we know 2 out of the 3 forces acting in the y direction. By simply summing these forces together, we can find the unknown reaction at point A. So again, this is going to be one equation, one unknown. So let's do that. So sum of the forces in the y direction are going to be 0. So the left-hand side here is equal to this quantity here, minus FD, negative because it goes down, plus RCY, we know that now, it's going straight up, plus RAY. Those are the only forces in the y direction. And if I continue to turn the crank and just do the simple algebra, I get that RAY is 350 pounds. That's this quantity here. It says here, please note that a negative sign in front of F sub D because the drawing shows the force is down. That's right. Positive is up, negative is down. So this should make sense. You should always check your answers for common sense. So RAY should have to push up with a larger force because the downward force is closer to it. So it's going to feel more of the burden there. Some of the x forces defined, that should say RAX. So 2 of the 3 red arrows are now known. And let's find the RAX. Because joint A is pinned, it is capable of reacting to a force applied in the x direction. However, since the only load applied to this truss, which is F sub D, has no x component, RAX must be 0. So if you just look at this free body diagram of the truss, you don't see any arrows other than RAX that are going horizontally. So the sum of all the forces in the x direction, that amounts to just RAX, and that equals 0. So nothing's pushing on our pinned support here in the horizontal direction. Now we're going to get toward the interior of the truss, and we're going to use something called the method of joints. We're going to use cosine and sine to determine the x and y vector components of forces. Of course, force is a vector, and any vector can be broken down into its component on 2 mutually perpendicular axes. Typically we'll use x and y. We'll use trig to calculate those components. Okay, we're going to assume all members are in tension. Again, we're going to work at a joint, and we're going to look at all the members that emanate from that joint, and we're going to assume they're all in tension. So if they're in tension, they're being pulled apart, and therefore, well, just a positive answer will mean that the member is in tension, but a negative number will mean the member is in compression. So that's how we'll determine compression versus tension. So you should convince yourself that if the arrows point away from a joint and you get a positive number, that means that the piece of steel that is placed there is in tension. So think about that for a while. As forces are solved, update the free body diagrams and use correct magnitude and sense for subsequent joint free body diagrams. So here we have a truss, which we know to be statically determinate because we've only got one reaction force here. This is the same truss basically. We know all the reaction forces, we've already calculated those, and now we want to work our way around to the various joints. Using truss dimensions to find the angles. If you'll notice here, we're just told that the distance from A to D is 3 feet, D to C is 7 feet, and from the line A, D, C up to the point B is 4 feet. But we don't know theta 1 and theta 2, so we'll need to find those. And the way to do that, of course, is using elementary trigonometry. We know that that distance is 4, so we can just move it over, and we've got a right triangle here. And I won't go into detail here. My assumption is that you can do this. If you can't, let me know. So the tangent is the opposite over the adjacent. So the tangent of theta 1 is 4 feet over 3 feet. Units cancel as they must. Tangent is a dimensionless number. So we get the theta 1 is the inverse tangent of 4 over 3, and that's 53.13 degrees. So we would update that on our diagram as 53.13 degrees. Now we're going to take a look at the other angle. We see that it's a right triangle as well, but it's got a longer adjacent term. And so the tangent of this should say theta 2 right here. This should say theta 2. So in the notes you're taking, make sure that says theta 2. And it is 4 over 7. And that gives us 29.745 degrees. So now I believe we know all the dimensions of our bridge. And that's the first step after finding reaction forces. Now let's apply the method of joints. So to apply the method of joints, we draw the free body diagram of each pin. So if you look closely, you can tell that this is our truss without the members showing. So we have point A, D, and C, and B. We have the angles in here. We don't really have to know the distance for this analysis, but we do need to put force vectors in the directions of the members and convince yourself that we have done so here. Every member is assumed to be in tension, and a positive answer indicates that the member is in fact in tension, and a negative answer indicates the member is in compression. Again, that may not be obvious to you at the moment, but you should convince yourself that that's the case. We can talk about it in class after you've given it some thought. So where to begin? Well, we choose a joint that has the least number of unknowns. That might be the easiest one to attack. Reaction forces at joints A and C are both good choices to begin our calculations because we know things about that. So we come back here, we've got these red ones, and again red, and the non-black ones mean we know what the values are. So we're going to start at those points A and C. We know that 350 pounds and 150 pounds go upward in a vertical direction. And so let's take a look at point A. So recall that it had 0 force on it. Let's look at point A. Recall that it had 0 reaction force here, so we can ignore that. So we've got 350 pounds going straight up vertically. We've got some unknown force AD, some unknown force AB, and we've got this angle 53 degrees. And let's take a look at finding AB. Well, we're going to start to use our equations. The sum of the forces in the y direction must equal 0. So what are the forces in the y direction? There are AY right here, and then there's the y component of the force that's in this member, which we're representing by the vector AB. So it's the projection of this vector on the the vertical direction. So that's 350 pounds. And then AB sine 53 degrees. You need to convince yourself, become comfortable with the fact that the y component of vector AB is AB sine 53.13. You need to come see me if that's not something you're comfortable with. At this point, we have one equation and one unknown. we can just do some algebra, and we're going to find that AB is minus 438 pounds. So what is the significance of the minus sign? Compression. We assume they're all in tension, pulling away like this. If we get a negative sign, they're in compression. This is something that we're going to find over and over again when we analyze different trusses, that this particular truss, which is at the end of the bridge, are always in compression. So we change the direction of the arrow, and we have 437.5, 438 pounds. So we update all the force diagrams based on AB being under compression. So we just changed it. Recall that a vector we can move around in the plane as long as we don't change its direction or length. So the green one now is the force due to the member here. And since this long bar is connected, the same force would be going in that direction as well, or at least acting at that at B as well. Okay, this is a method of joints here, so now let's work on AD. You can see we're slowly reducing the number of unknowns. So we need to find one of our equations, and the obvious one is F sum of the forces in the x direction sum to 0, because AD does not have a y component. So let's do that. So minus ABX. So there is an x component to this one since it's coming out at a diagonal, plus AD. We don't need any trig function there because AD is all in the x direction. And ABX, you need to convince yourself, is minus 237.5 times the cosine of 53.13 degrees. This is the basic trig that is needed to do this analysis. Come see me if you have problems with that. Plus AD, and if we do a little algebra, we get this. And finally we find out that AD is 262.5 pounds, and it's in tension because it's positive. So the beam that is at the end of the truss but is horizontal is being in tension. We'll find that most of the stuff at the bottom of the truss is in tension. That's the first indication of that. And we update the joint. Let's go over to C. Let's find out BC's force, internal force in that member. Let's start out in the y direction since we know the reaction force here. So RCY, which is 150 pounds, plus BCY, which is the y component of this one, equals 0. 150 pounds plus BC sine 29.745 equals 0. And then we can do the arithmetic and get minus 302. And as you might have expected, BC is also going to be in compression, as was the comparable one over on the other side. And so that's in compression, 302 pounds. So our member in here had better be able to withstand at least 302 pounds, probably much more for margin, and it'll be in compression. So it should be designed in, say, cross-section of the steel member so that it's optimized for compression. So let's update the whole thing, and we see that Yeah, we know that now. That goes out like that. And so what are we left with? Well, we're still on C because we don't know the black one here. Okay, it's starting to get repetitive, so hopefully you're getting the hang of it. And so this would be a summation of the force in the x direction. BCX, so the x component of this force here, plus, minus CD, because they're going in the opposite direction, equals 0. And again, you can do it on your paper, but you're going to get 262.5 for the force on CD, and that is in tension since it's positive. I believe point joint C is fully understood at this point. I don't think there's any unknowns there. That leaves us with up top at point D, and we don't know what BD is. So we're going to sum the forces in the y direction. So we have BD minus FD. So the only thing we've got acting on that joint, actually D is not the one up top. I believe it's the one, yeah, at the bottom, but just where it holds the load of 500 pounds. This one's the easiest one, no trig. And so it's positive, so it's in tension as well. So this vertical one in the middle is in tension. Is in tension. So I think we've exhausted all of the unknowns, and I wish I had a slide which will summarize all the forces on there, but I'm sure on the piece of paper that you've been following along with, you have the fully completed bridge, and you can, it's drawn out, and each of the forces that we've just calculated through the method of joints are written down on your paper so that you can have this for further reference. Thanks for watching.